What you're looking at right now is a reinforcement learning agent learning to play an RTS game, and that is the exact topic of today's video. So if I scroll up right here, oh, that's not scrolling up. There we go. What you'll see is that this is actually a notebook from a paper, and we could have looked at the paper, but I think the notebook is quite nice. It's clearly had some love put into it. So the name of this paper is Gym-micro, is that micro? I think it's micro RTS, toward affordable deep reinforcement learning research in real-time strategy games. So if you've been keeping up with reinforcement learning over the past couple of years, you've probably seen things like OpenAI's OpenAI 5 for Dota, which was where they had Dota agents that were playing, at a pro level. And then there was also Alpha Star from DeepMind that was playing at a pro level, StarCraft at a pro level. And those have all been super impressive achievements. So today I want to take a look at a paper that I happen to find while browsing Reddit that talks about how those types of agents learn and how they work, and what sorts of things are important when we're constructing agents to do this sort of thing. This is something that is kind of personal to me because I was actually doing one of these RTS competitions, and my agent never really worked. I spent hours and hours on it, and it kind of worked, but it was really bad. But after reading this paper, I think I actually figured out exactly what I did wrong, and it's giving me some really interesting insights. So without delaying anymore, I do want to jump into this and talk a little bit about what's important to these agents. So let's scroll down a little bit. And as we scroll down, we'll do an overview. The first thing I want to talk about is this environment they use. Here you can see live demos of this happening. So essentially what's happening here, right, you have a player in the top left right here, and you can see you have an opponent in the bottom right. They're gathering resources, creating units, and then sending those units to attack the other player. And I guess that's essentially how RTS games work, right? Except for this is a bit more simple than something like StarCraft, where you have to take in like pixels and a lot of complicated variables. This has really been simplified so that the authors could focus on, planning and really not have to worry about, also using too much compute, because the amount of compute like OpenAI 5 and AlphaStar use is just absolutely disgusting and not something you can really work with if you're a researcher without millions and millions and millions of dollars. So that's sort of what this environment looks like. If we scroll down a bit more, as you can see, they have a lot of examples, which I don't mind at all. They talk about some of the reasons why this can be very difficult. So I want to highlight some of these reasons, because the ones that are, I think, the most important to me, or the one that's the most important to me, is the fact that the action spaces grow combinatorially with the number of the units in the game. So what does this mean? So if we scroll back up for a second, you can see that they're creating units, right? And in these games, they have, sometimes 10 units at a time or so, which is quite a bit. That means you need to give actions for every single agent. But it can even be worse in like StarCraft. I know sometimes people will have like 40 units or something. I don't know the exact numbers. I don't play StarCraft, but when you have that many units, it can get so hard to figure out what to do, because you need to control each of them individually, or at least you need to be able to select a certain number of them, a specific array of them, and then give commands to that specific subunit. So it can be very, very difficult. And this is one of the things I really struggled with when I was trying to make an agent that did this sort of thing. So they do also talk about a couple other issues, things like the reward being sparse, having to generalize versus different agents, stochasticity, all that stuff is very difficult. Though I will say what I really want to focus about in this video is how you deal with so many units and having to choose from so many different actions, because that's really what I've struggled with. So if we scroll down, you can see they're talking about OpenAI 5, kind of just when I went over, and they explain the observation space and the action components. So this is very important, some very important legwork before we get into how this all works. So what you'll notice is that they have a certain number of features. So they have hit points, resources, owners, all these different sorts of things have a different plane, not a different plane, but they have multiple planes, right? So hit points, this is essentially a 2D array, right? So let's say if we go back up to the example, and let's say we have an agent on this cell right here. Well, in this cell, this would have 5 feature planes. Well, would have more than 5, but this specific cell would have 5 different feature planes, or feature values rather, for hit points. And because there's no agent here, there would be a 1 in the first plane, right? But if there was an agent here and it had full health, there would be a 1 in the 5th plane, or I guess the 4th plane, depending on how you look at it. Anyway, the whole point being is they break down this grid into a feature plane, and then that gets fed into the network. The more interesting thing, though, is how the action components work, and make sure to focus on this. I'm going to jump ahead in the paper a little bit to talk, or at least talk about something they talk a little bit about later, And that's how you choose actions. Because one thing they'll mention is that when you're trying to choose actions, you have to, one, be able to choose the right unit, right? So that's what this source unit is. You have to be able to choose the right unit. And that is very difficult when you're dealing with a grid that can be very big. I think in this case, they only use 16 by 16. And even when you're dealing with a 16 by 16 grid, I think that's 256, don't quote me, different possible units you could choose, even if not all of them are valid. And then for every single unit you choose, you have to choose an action type, right? Which is something like move, harvest. It's the high level action, what you want to do. And then for each of those actions you choose, you have to choose the parameters, right? So for harvesting, you have to choose whether you want to harvest something to the north, east, south, or west. And for each of these, that's the exact same thing. So this can be very, very difficult, as you might imagine, because essentially the way they do this, and I'm going to start drawing now, is let's say you have the base network, right? So you have your observation, and you put it into the policy, right? So the policy. So the policy now outputs an action. Normally, if we're just doing like a cart pull, right, you output one of two values, right? Or rather, you output two values, the probability of going left and the probability of going right. So this would be very simple, but in this case, we have to, well, how many actions do we possibly have, right? Well, we have the amount of source units times the amount of potential action types times the amount of potential move parameters. And once you multiply all these things together, the amount of possible outputs, I think for a 16 by 16 grid ends up, I think they said it was around 50 million different actions. And obviously that's not very realistic. We can't deal with that. So what do we do? How do we deal with this? And the key they've actually kind of illustrated here already in a sense by breaking these up. And that's the solution. We have to break it up. We have to predict differently for each of these what we want to do. So we will have one prediction for the source unit. So the source unit will predict something that's height by width. Then we have to predict something for the action type, which will have 5 different potential outputs. Then we will predict something for the move parameter, which will have 4 different outputs, and this was supposed to be 6. My bad. But you get the point, right? So for each of these, we output different things. And when we do that, instead of multiplying the dimensions of each of these together, we add them together. So we end up with something closer to like, I don't know, it would be like 300. I think it's in the 300s, which is a lot better than 50 million, as you might imagine. The issue that some of you might notice, though, is let's say we take this example, right? So let's say we select the unit at 1, 5. I'm just choosing a random position. And then let's say the action type is going to be a move. So that would be a 1. So we'd have 0, 1, and then all zeros. So that would, so far we want to select the agent at 1, 5, and we want to move it. And then we need the move parameter, and the move parameter might be, say, 1, 0, 0, 0. I forgot the commas. And in this case, this would mean we want to move to the north. So that's all good. But wait a second, we still have the harvest parameter. Oh, the harvest parameter, the return parameter, the produce direction parameter. We have all these parameters we still have to fill in, and we still have to output actions for all of those. So this is a little bit weird, right? Because it's like, what do we do? And the way they handle this is they just end up going with, I guess, because they have an action type and we know we want to move, we can ignore all the other parameters. So all the other parameters, no matter what we output, like 0.5, 1, whatever is outputted down here, this all gets erased out. So we only care about these first 3 because of the fact that our action type was to move. If we wanted to harvest instead, then we would ignore the move parameters and only focus on the harvest parameters. So I think this makes, hopefully this should make a bit of sense. That being said, there is actually still a little trick here that if we don't do later, we're going to get very bad performance. And I'm going to go over that in a bit. Now, before we do move on, I just want to ask very quickly, if you do enjoy this type of content, do consider subscribing. It means a lot to me and it really helps out the channel. I don't want to bug you too long though, so let's get back into it. So continuing on with this action space stuff, I think they explain here sort of what I just explained, essentially how we take the observation and we output an action. One thing you might have noticed though, is that this is just for a single action, right? And I guess we could just move 1 unit per turn, but that seems really inefficient, right? Imagine if you have 40 units and you can only move 1 every turn, whereas the opponent can move as many as they want. Well, you're probably not going to do so well. So how can we do this sort of thing for all the units. And they break down two different ways to do this. So the first one of those is this, let's highlight this, it's already bolded, but we'll highlight it, unit action simulation, which is called UAS for short, and GridNet. So both of these are actually, I think, pretty intuitive methods. So unit action sampling is just saying we'll take every single unit and we pass it into this, right? So we have a different observation for every unit and we pass each one into here to get an action for each one. I think in the case of like AlphaStar, if I'm remembering correctly, which is where they did what's it called, StarCraft, I believe they actually have like a recurrent neural network that decides which units it wants to select, and then when it wants to stop giving actions. They might do that for this paper. I forget the details, but the essential idea is that they run the network once for every single agent, whereas GridNet, they run the network once for the entire grid. So what that would look like is essentially they would have a much bigger policy, and the observation would be the observations for all agents. And then instead of just outputting one action, they would output an action for every single different grid space. Now, some of those aren't going to be valid because, right, if you look up here, there's only agents on so many grid spaces at once, right? So the actions that were outputted for this cell would be nulled out. The actions outputted for this cell would be nulled out. The actions outputted for this cell would be used, though, right? Assuming there's something there on that turn. So that's the general idea between both of these. And what you'll see in a second is they compare how these two different methods work. I've actually used GridNet in the past. I didn't know it was called GridNet, but that's what I used, and it didn't work at all. That being said, what you'll find out shortly is GridNet itself isn't necessarily bad, but there are some things we have to look out for. So if we scroll down, let's look at, we'll skip over some of the boring details, and we'll look at how these two networks actually perform. So to check how they perform, they measured them up against a bunch of different AI. So these AI they came out of a competition hosted for this environment where essentially different agents were pitted against each other, and the ones that won the most and got the highest ranking were, given the first place, second place, the higher rankings. So here you can see all the different agents they were matched against, and there's a good variety, it seems like. Although to be fair, I haven't seen how each of these perform. So here are the results for how UAS performs versus GridNet. So let's take a look at the top left of these first. So you can see that the best performance is right here. And let me switch this to red so it's a bit easier to see maybe, or blue might be easier to see in this case. So which one's easier to see? Yeah, probably blue. So right here, we can see that UAS at its best performance gets a 91% win rate, whereas GridNet gets an 89% win rate. So these are actually both really good because these are RL agents against agents that in the previous, in past competitions had won in first place, and other places too. But clearly, these are both performing pretty well. So even though they're pretty similar, UAS does a little bit better. What you'll notice is that the parameters, the amount of parameters in these models is very different. GridNet has about, about 15 times more parameters than all of the UAS models. And why is that? Well, remember, it's because for GridNet, we need one network that can output actions for every single grid cell. So the bigger the grid gets, the bigger this GridNet network is likely to get, which is not very good, right? It probably doesn't scale super well is the point. And what you'll see is that is reflected in the runtime, right? So the runtime, GridNet is taking about 2 times as long to run when compared to UAS, right? So that's not great either. Clearly, UAS is doing better here. And I guess that's not surprising when we consider just how beefy GridNet is, right? We have to predict actions for all these spaces where nothing exists. It's kind of a waste of our time. And I guess in that sense, it's good that UAS actually ended up performing better too, right? And I should mention that for these runtimes, they actually only use one GPU and a few CPUs. So this is not like a crazy compute that some companies use. This is a reasonable amount of compute. So that's awesome. We've kind of figured out UAS, GridNet. UAS is definitely the superior one in most cases. However, what about the case where they just use base PPO? So PPO is like a baseline reinforcement learning algorithm, right? And what you'll notice is that in both cases, when they just use PPO, they get a 0% win rate. And this is when I looked at this first, I was like, oh, that was me when I was trying to make my agent. I was trying to use like base PPO, and I guess no surprise, it doesn't work at all. Maybe this is kind of surprising. So the question is, what do they do between the best run and this worst run with just base PPO that makes the biggest difference? And the biggest difference, and I found this quite, I guess, a little bit surprising, was the fact that it has to do with this invalid action masking. Invalid action masking. What you'll see is that when they use invalid action masking, they get this huge jump here, down here, from 0 to 73% win rate. And down here from 32% win rate with partial invalid action masking to an 82% win rate with a full invalid action masking. That's a huge thing. So the takeaway here is if you're going to make an RTS RL agent, you need to use action masking, and it's probably the most important thing you can be doing. So what is invalid action masking? That raises the obvious question, right? And it's actually not too complicated. So if we scroll down a bit, they will actually delineate this in a little bit of a graph. So this might look a little bit complicated, but it's actually not too bad. What we want to pay attention to is we start at the feature map inputs, right? So this is the input to our policy. Once we input it, we get the feature mappings, right? So the feature mappings is just passing it through some network, and then the policy had to get our output action logits. So right here, we have the action, let's go back to the highlighter, we have the action type and parameter logits. So these are what decide what actions we're taking, right? It's what I showed earlier when I was drawing the, oh, I can't, it's off the page now, I'm too lazy to scroll over. But that's what I was showing earlier with the outputs of, like, you know, if we want to go east, then we want to have a 1 in the east position and zeros everywhere else. And we also get the source unit logits, and this is what decides what unit we select. The only difference that they're making for this invalid action masking is these, you see we have these masked action type, so masked action type and masked action, masked source unit logics and masked action type parameter logics. So essentially what's happening is for every action that's invalid, everything that we can't do, we're multiplying it by a mask that's 0, right? So we zero out all the logits that are impossible. So if we cannot, you know, for example, here's an example, right? Let's say we choose to do, I don't know, we want to move. Our action is to move, right? So this is like an upper level action, you could call it. And then for these, we need a bunch of parameters. So for the parameters, let's say we have, I'm going to draw a really bad grid right here. So let's say this is our grid, and our agent is going to be this blue thing right here. So our agent, if he wants to move, they can go left or they can go right. So let's say we output an array that looks like this, and I don't know, it'd be like 0.5, 0.1, 1, 1. So let's say these are the logits, right? And this is, we'll say the first one is left, this one's down, this one's right, this one's up. Well, we can't go right or up, so this 1 and this 1 are invalid. So what we'll actually end up with after applying the mask is 0.5, 0.1, 0, 0. And by doing this one thing, this single thing, and I will say, you know, to do this, you do have to know which actions are possible, which isn't something you always know, but lots of the times you do at the very least, in many situations, or at least you can predict it. It looks like my drawings got thrown off here, but from that one thing alone, we go from 0 to roughly 82% win rate. That's crazy. That's crazy. And this actually, I guess, isn't too uncommon in reinforcement learning agents. There actually are other papers that show that when you introduce a bunch of random actions into an agent and all these actions do nothing, they're just sort of to confuse it, they tend to get very confused. They tend to not work very well. And that's definitely one downside of the algorithms that we have today. And when you take that into account, maybe it's not so surprising that invalid action masking is actually incredibly important when it comes to playing RTS games, and there's so many different actions you can take, and the majority of them are usually invalid. So that was the biggest takeaway from this paper that I wanted you all to get. So hopefully that makes sense why we need to do that sort of thing, or at least if you're making an RTS agent. That doesn't mean that we will, you know, always have to do this. Hopefully one day we'll come up with algorithms that can get around this. I'm sure there's some work on this. I don't really know much about it, but that's a big takeaway. I will also go over some other, what I think are personally more minor takeaways. For example, diverse opponents. It's very important to have diverse opponents when you play, or at least it's pretty important. What they found is that when they went to play against, or when they matched them only against the best agents, they would learn to play against the best agents. But when they played them then again against the weaker agents after learning, they would lose to the very weak and naive agents, probably because the agents were, they were anticipating only the behavior of the very skilled agents. They weren't they weren't anticipating people to do stupid things. And that's something we've also seen in reinforcement learning. You forget what you don't learn, or you forget what you don't constantly do. So no surprise there, I guess. So nature CNN versus Impala CNN. I think this is just a matter of having a bigger network. I forget, but you just change your architecture a little bit, you get a little bit different results. Not too surprising there. And then if you want to, I highly recommend going and taking a look at this. I'm not going to go into it in depth now because I went over what I thought were some of the most important findings of this paper, but they do talk about how sparse return, right? So giving a reward only when the agent wins versus when the agent builds a unit or something, right? So when you add more rewards in to help the agent learn, that's called reward shaping. And while it has the benefit of helping the agent learn like more quickly usually, you're also incorporating more of your biases into it, right? The agent could oftentimes circumvent the actual goal if you reward shape, or it might not find the real optimal goal. So while sparse returns are better in theory, sometimes shaped returns are better in the shorter term if you're just trying to get results. So they talk a little bit about that here and how that affects it. One thing that's interesting that they talk about is how UAS and GridNet actually perform very differently in response to sparse versus dense rewards. So that's definitely something you can take a look at if you're interested. They also have a bunch of examples of their agent playing against other agents, and they also have a way to reproduce their results. So if this is something you're interested in, I highly recommend you go check it out. I thought this was a really interesting paper, a really good study, just getting at the core of what makes these algorithms work. Now, I guess some minor criticisms to talk about are, one, we can't tell if this will scale exactly to things like StarCraft because of the fact that they do reduce the complexity of the environment so much. It is possible that there might be extra tricks or something that are needed. Well, I'm sure there are extra tricks and things that are needed to get it to work. How well these baseline algorithms like PPO will scale, I guess we kind of already know that because we've seen it work for things like OpenAI 5, but anyway, it is different. It's something to keep in mind, right? It is much simpler. And one more thing I wanted to mention was the fact that they do use PPO here. I don't think they ever mention using a different algorithm for this. So it is possible that other algorithms will work a lot better without invalid action masking, right? And there's probably other ways that invalid action masking can be done even when we don't know what the potential actions are. There's probably ways we can build that into our models. So that's something I'd love to see in some follow-up paper. And there might already be stuff that exists like that. It's not something I've really looked into. But anyways, that's all I had for this time. So if you enjoy this type of stuff, you want to see more of these paper reviews or anything ML, AI related, especially RL related, do consider subscribing to the channel. It really helps out a lot. Anyway, thank you so much for watching, and I hope to catch you next time.